Hello and welcome to Lecture 5 on Electrochemistry. Today we're going to look at predicting redox reactions. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis for the bulk of the diploma exam questions that you'll see. Hopefully you're checking back with this page from time to time to get a sense of how your mastery of the material is coming along in anticipation of both your unit test and the diploma final. So far we've been looking at redox reactions and we've explained them in terms of the transfer of electrons. We're going to modify that thinking slightly and consider a competition for electrons between the reactants in a reaction vessel. Each species in the vessel is pulling in the electrons to some degree. Ultimately, only one can win that tug of war. In fact, we'll find that most species in the reaction vessel are electrostable. They neither gain nor lose electrons. But if one reactant can successfully pull electrons away from another, then a spontaneous redox reaction will occur. We can apply a spontaneity test or a spontaneity rule for all reactions we look at by reference to the electrical reduction potential table in our data booklet. And you'll need that for these questions. It's literally a hands-on exercise in terms of analyzing that table. And the rule is this: if the oxidizing agent in the system is higher than the reducing agent in the system in your reduction potential table, then a spontaneous reaction will occur. And if you think about it, the oxidizing agents are on the left-hand side of the table, and the reducing agents are on the right-hand side of the table. So we're going to get you to put your left hand on the participating oxidizing agent and your right hand on the participating reducing agent. And if your left hand is higher than your right hand on the actual page in the data booklet, then you'll know that the oxidizing agent will win the tug of war for the electrons and a spontaneous reaction will occur. And this is the process we'll employ to predict whether or not an oxidation reduction reaction will take place in any given vessel. In a number of these questions, though, they won't give you a complete listing of everything in solution. We'll need some rules to determine what, if any, other particles are present than the particles that they give you in the question. And those rules look like this. If they tell you it's an aqueous solution, or if they just use the word solution, you can assume water is present. Acidic solution, you can assume protons are present and water because it is a solution. And you note the subscript here is AQ. If it's a basic solution, you can assume hydroxide is present as well as water because we're in an aqueous environment. Some oxidizing agents and reducing agents work in combination, and if you scrutinize your reduction potential table, you'll see this to be the case. And then finally, some species act as both oxidizing agents and reducing agents. An example is water. You'll find it in both the left-hand and the right-hand side of the page. So we use these rules to analyze the contents of any given reaction vessel. And we determine the strongest oxidizing agent and the strongest reducing agent from all species present. Everything else we can ignore. If you consider what's happening, the electrons are being pulled on by all species in the system to some degree. But ultimately the strongest oxidizer will end up stripping electrons off the strongest reducer, and everything else will remain unaffected. Some intermediate strength oxidizers may gain the electrons temporarily, but ultimately the strongest oxidizer will strip the electrons off of these as well. After you've done this work, you can write a balanced chemical redox reaction for the system and make a determination whether or not a spontaneous reaction will take place. So here's an example. We have aqueous potassium permanganate reacting with an acidic solution of sodium bromide, and an orange-brown substance is produced. This orange-brown substance, this is characteristic of liquid bromine, so let's see what the reaction looks like. Our first step is to list all species present. So potassium permanganate in an aqueous solution. Potassium permanganate is soluble in water, so we represent it as free ions like this. And there's our water. We're mixing it with an acidic solution of sodium bromide. So there's our acid. And of course, sodium ions and bromide ions are as free ions in solution because, again, they're soluble in water. Our next step is to list all the oxidizers. And I'm not pulling this out of thin air. I'm simply referring to the reduction table in the data booklet. Anything found on the left-hand side of the page, I designate as an oxidizing agent. And so these are the oxidizing agents. Anything on the, and I wanted to make the point that the permanganate by itself is not on the left-hand side of the page. Only in the presence of a strong acid is permanganate a strong oxidizing agent. So that's why you see the line linking these two. And these are the reducing agents, which are on the right-hand side of the data booklet page. Water is a reducing agent, and the bromide ion is a reducing agent. So after we identified all the oxidizers and all the reducers, we identified the strongest oxidizing agent and the strongest reducing agent. So here I've reproduced my list from the previous page, and you'll see that the permanganate in acid is the strongest oxidizing agent. It's the highest on the left-hand side of the page, the highest oxidizing agent. And the bromide ion is the strongest reducing agent in the system. It's the lowest on the right-hand side of the page. So then we write half reactions. The strongest oxidizing agent goes through reduction, and that looks like this. This is our reduction half reaction, and I've simply transcribed this from the data booklet. The strongest reducing agent, the bromide ion, goes through oxidation. So I have to take the reaction as it's written in the data booklet, and I have to flip it. In your data booklet, you'll see it's written as a reduction, but I need to flip it to represent it as an oxidation, like this. Our next step is to balance the electrons by employing multipliers. So the reduction half reaction has to be multiplied by 2, and the oxidation half reaction has to be multiplied by 5. In the end, we're left with these half reactions with 10 electrons going into the reduction and 10 electrons coming out of the oxidation. Of course, those cancel, and what we're left with is the net redox reaction. We then do a right-hand, left-hand test on the reduction table in the data booklet to determine whether or not a reaction is going to take place. And I've just transcribed a bit of your data booklet on the right-hand side of the page here. I've written down the strongest oxidizing agent on the left and the strongest reducing agent on the right. And you literally put your left hand on the oxidizing agent and your right hand on the reducing agent. If your left hand is higher, then you can assume that the reaction is spontaneous and electrons will flow from the bromide ion to the permanganate. And indeed, your left hand is higher, so you will see electrons flow in this system, represented by this arrow, and we represent that further by the designation spawn above the reaction arrow. The question talked about a brown sludge forming in the system, and that was our liquid bromine coming out of the reaction. You notice there's a lot of water being produced here, but that's extremely hard to detect. Go with the production of the bromine as the orange-brown sludge as your determinator. Let's do one more. Hydrogen peroxide mixed in a solution of silver nitrate. So again, let's list everything present. The hydrogen peroxide is in molecular form. It's in your data booklet on the reducing agent side. Silver ions and nitrate ions. And we're writing these as free ions because, of course, silver nitrate is soluble in water. And the question does talk about a solution, so water is present. These are the oxidizers. Silver ions and water are listed on the left-hand side of the reduction table. These are the reducers. Peroxide and water are listed on the right-hand side of the table. We then identify the strongest oxidizing agent and the strongest reducing agent. The strongest oxidizer is the silver ion. The strongest reducer is the peroxide molecule, in fact. So we write out the half reactions for these, and we take those half reactions from the data booklet. The strongest oxidizing agent goes through reduction. So we simply transcribe this. I've lost my mouse. There it is. We transcribe this half reaction from the data booklet. The strongest reducing agent goes through oxidation. In the data booklet, of course, it's written as a reduction, so we have to flip that half reaction to write it as an oxidation, just like this. We have to employ multipliers as the next step to cancel out the electrons, so the reduction has to be multiplied by 2, and the oxidation multiplied by 1. And then we add the half reaction together, and we ensure that the electrons are cancelled, both in the reduction and in the oxidation. So this is our overall redox reaction right here. and we check for spontaneity, and we do that in the same method with the left-hand, right-hand rule. Here's the silver ion as it exists in your reduction table, and here's the peroxide molecule. So you put your left hand on the silver ion in the reduction table, and your right hand on the peroxide molecule in the reduction table. And if your left hand is higher, then electrons are going to spontaneously flow. And in fact, your left hand is higher, so this is a spontaneous redox reaction, and electrons will flow from the peroxide to the silver ions. We designate that with the indication spawn above the arrow. If we look at the chemical system, we'll see a couple of things. First of all, silver atoms come off as a gray-silver sludge at the bottom of the reaction vessel. Secondly, we'll see bubbles as oxygen's formed, and you can test those with a pop test. And then, actually, I think it's a flame test. And then finally, we're producing an acid, so the pH of this system should go down. And those three tests would be confirmatory for a spontaneous chemical reaction. So that concludes my lecture. I'll refer you, of course, to any homework your teacher assigns, and hopefully you found this of some assistance. And we'll see you next time when we talk about standard reduction potentials. Thank you.